Chapter 5, Think and Rank, problem number 31. A van exerts a force on trailers of different mass m compared with the force exerted on each trailer. Rank the magnitudes of the forces each trailer exerts on the van. This is an awkwardly worded question. It's basically, there's only one answer that would make any sense just based upon the bizarre wording. But it's trying to get across the idea that no matter what the mass in the van or the speed or any of that other information, whatever force the car exerts on the trailer is the same force, same magnitude of force that the trailer exerts on the van. And so ultimately, the pairs of forces are equal in magnitude within A, equal in magnitude within B, equal in magnitude within C. That's ultimately what they're going for there. Yeah, it is what it is. 32, you have a bunch of boxes there, and they all have the same mass, sliding on a friction-free surface. And the reason they have that is so that the only force, the horizontal force acting on it, is this force F, as it's shown in the picture. So rank from accelerations. Well, A has only one box. It has one box being pulled with a force. B has two, and C has three boxes being pulled with a force. So the more mass you have, the less acceleration there's going to be. Acceleration is inversely proportional to the mass. So if we ranked accelerations, it'd be ABC, because as you can progress with A from B to C, you're increasing the amount of mass being pulled. The tensions in the rope connecting the single boxes. Well, in A, there's a single box, F. In B, you're going to have half the force, because the force F is pulling two boxes, and so if only one box is being pulled, in case B, you have half of the force. And then in C, you're pulling three boxes with the full force, two boxes with 2/3 of the force, and then one box with 1/3 of the force. And so if you ranked them in terms of the tension and the ropes connected to the single box to the right, it would be A, B, C. Now, the question only asked for B and C, but I threw that A in there just for a bonus. Number 33, three identical pucks are sliding across ice at a given speed. The forces of air and ice friction are negligible. Rank them on the force needed to keep them moving from greatest to least. This is Newton's first law, and I believe that you actually, for problem 34 on page 36, is the exact same problem. Objects in motion will stay in motion unless acted on by some outside force, net outside force. So you have weight and you have normal force acting on each puck. They will balance each other out, neutralize each other. The three pucks are going to be moving to the right. It doesn't take any force to keep them going. They are in equilibrium. The total force is zero. Acceleration is zero. Change in velocity is zero. And so, yeah, I'm not quite sure why this is a Chapter 5 problem, but you should know how to do it. Then rank the pucks by the force needed to stop them in the same time interval from greatest to least. So the faster one is going to require more force to stop it in the same amount of time. So just imagine that, not wanting to get too violent, but you're Superman, and you're wanting to stop a bus coming right at you. You have 1 second to stop it. Well, it's going to be a lot harder to stop a bus coming at you at 100 miles per hour than one coming at you at 40 miles per hour, or one coming at you at 2 miles per hour. The faster it's going, the more force is required to stop it in the same time interval. Now, I do want to throw in that they throw in the same time interval because that becomes the key to a question that shows up in, I believe it's Chapter 6. And if it's not Chapter 6, it's Chapter 7. I'm pretty sure it's 6. Anyway, that's the Think and Rank from Chapter 5.